We will start the journal club now. Today's presenter is Soo-Min Kim. In this session, we plan to cover continual learning, and the title of the paper is Continual Learning of Context-Dependent Processing in Neural Networks. The presentation is expected to be lengthy, so if you have a question, come to room 315 after the presentation. I have one question. What is continual learning? In a intelligence system, which is an intelligent system that revolves around the model that is the subject of artificial intelligence, learning is it becomes the basis of the given data environment. When external stimuli change, various organisms, including humans and continuous, collect information throughout this and go through a process of updating or accumulating existing knowledge in the form of modifications. In the case of the static model that assumes the general offline learning, it can be seen that the learning framework and the inference framework are separate, which has a clear limitation in that big data that can be generalized for learning is defined as the train domain. There is no choice but to have. For example, even if it is simply a categorized or classification problem, even if a methodology for a data augmentation or multiple model generalization is applied, it is still a classification within a defined category, and all data in the open world in the model representation. It cannot be contained, can be seen as a limitation. Maybe you can think it is natural that the performance increase as the data used for model generalization increases, and this research itself must be developed for future artificial intelligence. However, the scope of artificial intelligence that we pursue will always include not only the server, which is the entity that provides the service, but also edge device, and if that happens, it will not be possible to handle the increase in model parameters accompanying the increase in data used for model generalization. It would be natural. Therefore, the problem implied by continuous learning is needed. So these pages show why continual learning is needed. These pages show the problem statement about continuous learning. And first thing is the changes in data distribution. When we are using the continuous learning, a change in a data distribution can refer to a shift in either the data domain or label domain. And then second thing is the phrase studying continuous learning covers a wider range of settings than one might initially think, given the diverse scope of continuous learning itself. And then these pages show the following typical scenarios for continuous learning. Firstly, I talked about instance incremental learning. Instance incremental learning can be defined like this image. During the training phase, batches of samples for a single task are received. And then in this scenario, the input data set is continually fed into the deep learning training algorithm. And when dealing with the single task, there is no need for task-specific identification. And second is the domain incremental learning. It is assumed that there are multiple tasks or sharing the same data level space, but it is only different in their input distribution. Despite not being a single task, the reference path does not require the task-specific identification, as with instance incremental learning. So it is the different from before. And third is the task incremental learning. Task incremental learning is defined like this image. Each task has a separate data label space that does not full overlap. Additionally, task-specific identifiers are provided during both training and testing. In the reference path, task-specific identifiers will be available as previously mentioned. And the next thing is the class incremental learning. It is each task has distinct data label space that does not completely overlap. During training, task-specific identity is available, but in inference timing, a task-specific identity is not available. Yeah. And so the next is the task-free continual learning. During the training phase, batches of samples for a single task are received. In this scenario, the input data set is continually fed into the deep learning training algorithm. When dealing with the single task, there is no need for task-specific identification. Yeah. And then next thing is online continual learning. It is defined like this image, and then each task has a separate data label space that does not fully overlap. Therefore, even if task distinction is not necessary, all batches follow the single stream framework, making training tasks independent. In the inference phase, task-specific identifiers are optionally available under the certain circumstance. Next is the blood boundary continual learning. We assume that the boundaries of the task are blurry, and we mean a scenario with some overlap rather than disjoint data levels. In other words, it is all the same as the class incremental learning, except that the data label space must be partially overlapping. Therefore, task-specific identifiers cannot be used in the reference path. Yeah. And then final is the continual pre-training. Final is the continual pre-training. And then it can define this sentence. This text describes a scenario where pre-trained data is receiving in a continuous sequence to enhance the performance of downstream tasks throughout the good representation. And then as a result, task-specific identifiers, which refer to the task level of the downstream task, are unnecessary. Also, this task is always I show you when I have a lab meeting. So and then next part is the methodological approaches. And then you can show the image, and this image show The main approaches, the five things: regularization, regularization-based approach, replay-based approach, optimization-based approach, and then representation-based and architecture-based. Regularization-based approach is the first thing um, I deal with, and then the aim is to include an explicit regularization term to balance the old and new task. Um, the key aspect of the regularization of the use of the pre-trained model as a reference for compression. Then the initial technique for regularization is weight regularization. This method allows for selective regularization of change in network parameters. Let's see. And next thing is replay-based approach. This approach have three kinds of things. First is experience, second thing is the feature, and then last is the generative. When learning a new task, method of the recovering and approximating old data distribution can also be considered and are divided into three types depending on the subject of replay. And first thing is implemented by having a small memory buffer and storing training samples for some previous tasks in it. Of course, because the storage space is limited, the main solution is to solve the problem of how much information to store. And then second thing, feature replay. It has an advantage over the experience replay in terms of capacity, but the problem occurs that the representation of the same sample changes as the feature extractor is updated. This soon leads to a story where replay at the feature level carries the risk of catastrophic forgetting. As a way to solve this problem, feature distillation between the old model and the new model is used. And then last is the generative replay, which is a strategy of using the learning data of the old task for replay using a generative model. Various structures such as VAE and GAN are used. There is no significant difference in the method itself, so I will briefly mention it here. And ultimately, what replay-based approaches have in common is that they prevent catastrophic forgetting by directly or indirectly using information about input samples or representations used in existing learning as the task is learned. The regularization method or reply introduction earlier was ultimately a method that could use previously learned data implicitly or explicitly. A method of the explicitly changing or adjusting the optimization structure was introduced, breaking away from the keyword existing, and this can be grouped into a larger framework called an optimization-based approach. And the most common idea is gradient projection. And some replay-based approaches have adopted a method of aligning parameter updating according to the updated direction of the experience replay, which has the effect of maintaining the implicit space and gradient space formed by the existing input when parameter updates or for a new test are made. When it comes to robust optimization for multiple tasks, you can think of meta-learning from a similar perspective. As expected, meta-learning also falls under the continuous methodology. This page shows the architecture-based approach. Um, Most of the methods mentioned above before were solutions to how to utilize shared parameters in multiple tasks. But however, when a single parameter is employed in multiple tasks, there is a disadvantage that is fundamentally difficult to solve: the interference problem. Unlike this existing method, this paper approach architectures as a way to solve the interference problem by learning task-specific parameters independently of shared parameters. However, recently, it seems that instead of categorized it this way, it is categorized into three categories: parameter allocation, model decomposition, and modular network. Parameter allocation is an extension of parameter isolation, and then model decomposition is an approach that involves breaking down a model into task sharing and task-specific components. It is generally assumed that the task-specific component is a scalable network, which is consistent with previous research. This page shows the last thing is modular network. The modular network is a structure that suggests a pattern subnetworks or submodule within the existing network. The progressive network paper proposed using the same network for each task and presented a method for transferring knowledge between different subnetworks for each task and presented a method for transferring knowledge between different subnetworks through adapter connections. And then it has other approaches, but you can read this page when you have any interest. Yeah, page is the conclusion, and this page shows continual learning is different from the way the brain actually perceives and thinks. This is because what a deep learning model learns is not the memory of the experience itself, but the representation between neurons that can map that experience. Therefore, we face the problem of being easier to forget and more difficult to teach. The main goal of continuous learning is how to incorporate new contents without the disturbing previously thought. And finish today's journal club. Thank you for listening.